Hey everyone, this is Dr. Walker. This is video 239. It's called Batteries and EMF. Let's start off this video with a question. How does this happen? You can light up a bulb with a potato. So you can't light up a big bulb with just one potato, but if you hook up 3 potatoes together in a certain way, you can actually light up a very small light bulb. So any thoughts about how this is possible, please put them in the comments below. Let's start off this video with a little bit about batteries. So what happens inside a battery is that there's electrolytes and there are chemical reactions occurring that are able to separate the positive and the negative charges. So in essence, you have a continuous supply of charges at the positive terminal. So in this case, all the positive charges can accumulate here on top, all the negative charges at the bottom, and by keeping separated due to the chemical reactions that occur, these positive charges, they're going to go through the circuit all the way back to the negative terminal. So by allowing charges to separate within a battery, that's how you have a potential difference in a battery, and that potential difference is providing energy to the charges so that they can go through the circuit. So that's just a very simplified description of what happens within batteries. And now we can talk about EMF. EMF, it stands for electromotive force, but it's not actually a force, it's actually a voltage. You notice that it has units of volts. The definition of EMF is the energy per unit charge provided by a source such as a battery or a generator. So a battery will provide energy to the charges so that they can move. How much energy per charge that they provide is the EMF. Now this may sound familiar because we defined potential difference as the change in potential energy per charge. So you may be wondering, well, what's the difference between EMF and potential difference? So if you have an ideal battery, which is what we have in most of our circuits that we're dealing with, we simplify things. If you have an ideal battery, then the EMF that it provides is actually the same thing as the potential difference across that battery. So for an ideal battery, EMF and potential difference, there's really not a big difference. However, one more thing before I move on. The rating of a battery is the battery's EMF. So if you have, let's say, a AA battery, right, AA battery, you may have seen that it says 1.5 volts on the battery. If you haven't seen that, take a look. So 1.5 volts is actually the EMF of the battery. If it were an ideal battery, then that means that once you hooked it up to a circuit, such as a resistor, that you would get a potential difference of 1.5 volts from that battery. But it's not an ideal battery. So actual batteries actually have an internal resistance. So in this slide only, we're going to be talking about more non-ideal batteries, and we're going to consider the fact that they have an internal resistance. But after this, whenever we have circuits, we're going to go back to our ideal batteries where the EMF and the potential difference are the same thing. So considering an actual battery that has an internal resistance, if you look at this yellow rectangle, that's the whole battery, the whole thing. So the whole battery has the EMF, right? It has the energy per charge that the battery is providing due to the chemical reactions occurring. But there's an internal resistance within the battery. What this means is that there's going to be some energy lost when the charges move through that internal resistance. When they move through, they collide with the atoms in the resistor heats up, that energy is lost to the surroundings. There's energy lost across this resistor as the charges go through the resistor, then that means that there is a potential difference across the resistor. Using Ohm's law, we know that I is delta V over R. So we know that delta V is I times R. So in this case, the potential difference across the internal resistor with small r is I times little r because the resistance has a little r. Okay, so what this means, if we take a look at the notes here, the terminal voltage of the battery is less than the EMF when the battery is connected. So again, the whole thing is the battery. The terminal voltage is the voltage that you get from A to B. That's how much voltage you get out of the whole battery. I'll call that one delta V. I know I called this one delta V as well, but we can call it delta little v instead of delta big V. So that was IR. So let's take a look at how much terminal voltage we're going to get from our battery. We're going to call that delta V, big delta V. So we're going to get the voltage from the EMF. Remember, EMF has units of volts. There is a potential difference here. There is a delta V. But we're going to lose some voltage across this resistor. We know that we lose this voltage because we know that we lose the energy. And we also know that if, let's say this is a 9-volt battery where the EMF is 9 volts, we know that our wire here, all of these points on the left are at 0 volts. We know all of these points here at 9 volts. We know that our voltage has to drop all the way down to 0 volts by the time we get to the other end. So we know that we lose voltage as we go across both resistors so that we get down to 0 volts. Okay, so that being said, the terminal voltage is going to be the EMF minus the voltage difference across the internal resistor, minus IR. So the terminal voltage of the battery is less than the EMF when the battery is connected. So there is a difference between terminal voltage and EMF. One more note about this. Let me rewrite the equation here. Delta V is EMF minus IR. The EMF does equal the terminal voltage when no current flows. This note comes straight from this equation. If the current is 0, then this term crosses out here and we have that the terminal voltage delta V is the EMF. So, to summarize, the rating of your battery is the EMF. That is the terminal voltage if it's not connected. That's when no current flows. But usually you're going to connect that battery to something else. So once the battery is connected, for example, to this big resistor R here, then the voltage that you get from the battery is not the full 9 volts anymore. It's going to be less. Using this equation, you can find out how much voltage you're actually going to get from the battery. Let's do an example. This is your turn, but it's really just an example. I just wanted to keep it within this video. So we have a 6-volt battery. So that's the rating of the battery. You read that, you say, okay, that's the EMF. With an internal resistance of 1 ohm, that's little r. It's connected to a load resistor. The load resistor is just the big R resistor that your battery is connected to, just like in the previous circuit. You've got the EMF, you've got the internal resistance, then you have your R. The battery is this whole thing. This is your load resistor. We just call it load resistor just to differentiate it from the internal resistor, little r. So, find the voltage across the battery terminals when there's a current of 2 amps from the negative to the positive terminal. So there's a current of 2 amps flowing through this whole circuit. What is the voltage across the battery? That is the terminal voltage. That's what we're looking for. The terminal voltage is the EMF minus IR. So 6 volts minus the current is 2 amps times the internal resistance was 1 ohm. 6 minus 2 is 4 volts. So hopefully this clears everything up. The terminal voltage is 4 volts. That's what we get from this battery once we connect it to this resistor. The actual rating of the battery is a 6-volt battery. That's how much voltage that you get if it's not connected to anything. So that is all. Next video is going to be something new. I hope you find it fresh and exciting, just like I do.